Right. So, hi everyone. Thank you for having me here. My name is Dimitrios. I'm from Greece, and here are a few things about me. So, I have a degree in computer science with focus in cryptography, and I'm engaged in computer security since 2002. I was actually a member of one of the first reverse engineering groups back in Greece. I started my career as a network security engineer for about 10 years. Then I moved into developing for almost 5 years, and the last 5 years I focused mainly on Android security. While before I joined Microsoft Defender research team as a senior security researcher, I was leading a team which was conducting malware reviews for the Google Play Store. So let's jump right to the outline of this presentation, which consists of the following topics. So first of all, we're going to have a brief overview of the fundamental principles of the intents. And then we're going to talk about data and file sharing the Android operating system using content providers. Share targets, definitions, usage, and mainly how to identify share target. Then we're going to move to the main topic, which is the dirty stream attack. We're going to identify the root cause of this vulnerability pattern and see how a third-party app can actually exploit it. Then we're going to talk about the actual impact, which may vary from, let's say, information disclosure up to code execution. And at this point, we're going to see an actual code execution case. And finally, we're going to see some mitigation ideas on how to protect Android apps from this or similar type of attacks. All right, so as most of you probably know, intents are the high-level solution, Android operating system's high-level solution when it comes to inter- and in-process communication. So they can be used to start activities, services, or deliver a broadcast to a receiver, or more general, to communicate an action to an internal or external component. And these, let's say, carrying along various type of info like a request, category, data and its type, flags, which can be used to modify the receiver's, let's say, behavior. So we have many ways to categorize them, although one of the most, let's say, important is if they are explicit or implicit. So in case an intent is explicit, it defines categorematically the component which targets, where in case it's not implicit, the system will identify the, let's say, the most appropriate component based on what we call intent filter. So intent filter is simply an entry in the Android manifest which defines some characteristics of an intent that should be sent to a specific component. And finally, we have the pending intents, which are simply, let's say, objects that wrap other intents and can be sent to an app in order to perform an action in behalf of the sender. That was all about intents. So, as you also probably know, Android apps are sandboxed, each one trapped in its own data space and memory space. So that makes data and file sharing between Android apps quite hard. And to make things more easier, the Android operating system provides what we call content providers. So an app which wants to share some data creates a content provider. Another app which wants to access some data creates a content resolver, which is a proxy object that's going to communicate with this content provider. And for this process to take place in the background and not block the main thread, we can use a cursor loader. And the result of this query can be, let's say, accessed using a cursor object, which is returned from the remote content provider. Now, what I just described here can be easily visualized in this figure. So on one side, we have the server, which wishes to share some kind of data that can be structured data or a file. So it's going to implement a content provider and add methods which can be used in order to query, insert, update, or delete data. Now, on the other side, we have the consumer, which is going to create a cursor loader, which, again, is going to communicate with the resolver. And since the resolver, as well as the provider, implement the same interface, so the resolver has also to create methods which can be used in order to query, insert, update, or delete data, now on the remote content provider. So after this point, these two ends are, let's say, ready to exchange data. Now, when it comes to, oops, have an issue. Sorry about that. Oops. Okay, small break because so right. All right. So when it comes to the code applications level, content providers are one of the earliest created components. So if we start from the activity thread in the main method, when an activity thread object is created, a looper and a handler are going to be associated with it. And the first step is, one of the first things is to bind the application with the newly created process. So the bind application method will send a bind application message to the message handler. And this is going to call the hand bind application, which is going to call the install content providers, given a list of the content providers that this application wishes to implement. So for each one of them, is going to call the install provider, which is going to create a content provider object and attach info about the application to which this content provider belongs, to the name of the class which implements the content provider. And one very important, let's say, property here is the authority, which defines, let's say, identifies this content provider system-wise. Now, when we come on the consumer side, things are pretty much straightforward. So simply acquire an instance of the application content resolver and use the query method, one of its overloads, in order to query data on the remote content provider. So here, just to one of the most important arguments, the first one, which is the content URI, which consists of the content scheme, the authority, the one I said before, the table name, which can be used in order to narrow down our query to a specific table. And finally, we have the file name, in case we're dealing with a file provider. I'm going to explain what is a file provider in the next few slides. So another important, let's say, argument here is the projection, which is actually defines the column. It's an array of strings with the column names of the remote content provider that we want to query. So you understand we have a similarity with an SQL database and this one. So the result from this query can be retrieved using the get method of the cursor object. And finally, we can just process it. Now, while file sharing can be achieved using content providers, common content providers, the Android operating system uses a dedicated class for this thing. So we have file providers, which is a subclass of the content provider. And that being said, Android apps can now use content URIs, which are, let's say, more manageable, more secure instead of the well-known file URIs. Now, besides extending the file provider class, besides adding the entries in the Android manifest, one very important step that someone has to take in order to share files in the Android operating system is to create what we call an XML files path file, which actually looks like the one I have here and can be used to map file URIs to content URIs, right? Next, we have the open file, which given a URI will return a file descriptor. And finally, we have the open asset file, which can be used to return subsections of files. Now, let me elaborate a little bit more on the files path file, which is an XML file, actually, that has a root element which is called paths, and some child elements like the root path and the others that I have here, which, let's say, represent directories which are commonly used from Android apps. For example, we have the root path, which represents the file path, the root directory of the device, the files path, the internal files directory, the cache path, the internal cache directory, and so on. And we have some attributes like the name, which can be used to represent the specific child element within a content URI, and the path, which can be used in order to, let's say, define subdirectories within the directory that this child element represents. And if this sounds a little bit confusing, I have some examples here. So this one simply will point to the file, to the root directory, this one to the external directory, and a more complete example, we have the scheme, the content URI, which you have the authority, then you have the test root, which will point to the root directory of the device, so then you can simply add the path to the internal directory, and you can index files within this private directory. Now, when it comes to common consumers, we have a couple of more functions, the methods that we have to use here. So we have the open input stream, which given a URI can return a file descriptor, and this can be then cached to the external and internal directory and finally be processed. Now, common apps which are consumers are editors, mail messengers, and many more, actually. So during the beginning of this presentation, I said that one of the most, let's say, important things when it comes to sharing data with content providers is that they are more secure, and they're actually the suggested way of doing that. And this is where the permissions come into place. So, for example, for system providers which share data that have to do with user private info, like SMS, call logs, and all these things. An app needs to have specific permissions. For example, for the content SMS provider, you need read or write SMS. For the contacts, you need read write contacts, and so on. Now, when it comes to third-party apps, what is very important system-wise is if a content provider is exported or no. So if it is exported, any app which is installed in the device can access the provider, while if it's not exported, only apps with the same user ID can access it. Now, can we make this, let's say, behavior more manageable? Yes, we can. We're using the specific, let's say, attribute here, which is called grant URI permission. So that being said, an app can simply create then an intent, add this flag here, which defines the mode of operation, and attach a stream to this intent, send it to another app, and provide temporary access to the specific file. All right, so another thing is if this grant URI permission is set to false, then we need to take some extra steps in order to, let's say, share some files. Now, another way, the last way to, let's say, to share some, actually to provide access to a URI is the grant URI permission, which takes a package name, the URI for which we want to share, to give access, and the mode of operations. Although, anyone notice something strange regarding this method? Something that doesn't stand so well here? No? Anyway, so yeah, I mean, you should have some more context, I guess. So it actually provides access based solely on the package name, right? So you just give the package name, doesn't perform any signature check, so it doesn't, let's say, verify the source of this package and simply provide access there. So you can simply create another app and, get access to this one. Actually, this is one of the first, when I'm checking for vulnerabilities when it comes to content providers, is one of the first codes that I will check. All right, so this brings us to our next topic, which is shared targets. So shared target is an Android app which defines itself to process files or data which are sent from other apps. All right, so examples are file, image, video editors, mail clients, social network apps. We have a lot of apps which can be shared targets. And there are main three ways for an app to receive data from another one. So the first one is to use an activity which will match a specific intent filter, or to use the chooser target service, or to use the sharing shortcuts API. In this briefing, we are going to focus on the first one, which is the most, let's say, commonly used. So we have an activity which will handle the incoming file. And this activity should be declared in the Android manifest and has very unique characteristics. So it has a filter which filters for actions sent or actions sent multiple in case the app handles more than one files at a time. And another important characteristic here is, of course, the data, which defines the file type that this activity will handle. Right? So, for example, this one will handle image type files. Right, so how we can send a file there? Create an intent of action sent, add the file that we want as an extra stream, then we just define the type, and then we are creating a second intent out of the first intent, giving the first intent as an argument, and finally we can use the start activity, adding this second intent as an argument. So if you put all these steps down, you have something like that, the code we have here. So starting from step 1 up to 5, you create the intent, you attach the stream, you set the type, create the chooser, and start the activity. Now, what is going to happen when you, let's say, execute the specific code is that the system is going to trigger the share sheet dialog. So this is a dialog which is used in order for the user to choose the component that this file should be sent to, right? And this is because this intent is actually implicit, so it doesn't define the component that we want to send this file, so the user has to take the call and, choose the component that we should send this file. And actually, this is a practical way for you to identify which shared targets you have in your device. You can simply, long press a file, then choose share, and this dialog will show you how many shared targets you have in your device. Right? So when it comes to handling a stream, out of, let's say, more than 90% from the apps that we have reviewed have about the same way of handling a stream. And this is the following one. So first of all, try to get the file name of the incoming stream. That's the first step. And to do that, perform a query to the remote file provider, and project the display name. Why the display name? Because it's the one which is used from the file provider, the default file provider of the system. So makes sense that the developer thinks that deals with a file provider, so it's going to project the specific column. So what is going to be returned from this, let's say, query, is then used to create a temporary file, a cache file, where then create an input stream out of the incoming URI, and finally create an output stream out of the file that was created before, right, the temporary file. Finally, copy the input stream to the output stream. So that's about it. Like I said, almost every app uses about the same steps. So just keep in mind here that both the URI as well as the file name are controlled, of course, from the sender. All right. And this brings us to, let's say, our main topic, which is the dirty stream attack. So the idea is the following. On one side, we have the rogue APK, the malicious APK, say it the way you want. And the other side, we have the shared target. So the first step is to create a process file request. All right. Next, as we saw, in most of the cases, the shared target is going to ask back for the file name. And in some cases also about the size. And since we control both these values and there's no system check or something, we can send whatever value we want. We can just craft a string, send it there, size, send whatever we want. Then it will ask for the file descriptor, actually it will call the open input stream. And since we control also the content of this file, we can also send, again, whatever we want. Now, this attack here reminds a lot of the file upload, let's say, flow when it comes to web apps. So you intercept the request, you change the content, you change the file name, you change everything, you send it to the server and see how the server will handle the specific request. So it's about the same. Although here we have the advantage that we are able to see, we can do some kind of a source code review to see how the shared target will actually handle this stream. That's the advantage here. All right, so let's put these steps down and create our rogue APK now. So we're going to create a content provider of ours, right? Because we want to share a file. Now we're going to send one, so we have to have it somewhere. And we're going to share a malicious payload. We're going to modify our content provider in order to send a mal-crafted string back in case it gets queried. And create an explicit intent. We don't want any user interaction, so we just can spawn our intent at any time. And finally, attach the payload as a stream. Since, like I said before, we control the stream. All right, so how will you do that? So we're going to use a content provider instead of file provider in this case. We're going to implement a couple of methods here, which the default file provider has. This is the query, open file, open as file, and so on. So when it comes to the query, how we do that? First of all, we are going to add columns which are exactly the same like the one that the file provider is using, or at least almost the same. So we're going to add display name, size, data, whatever query we might get from the shared target. And then we are adding a row dynamically depending on the incoming URI. So why we do that? We do that to make this content provider more general, let's say, be able to handle different cases of shared targets. It's going to make sense at the end of this, let's say, code flow, but for now you can keep in mind that we can, like I said, add a row dynamically depending on the incoming URI. And actually depending on query parameters that we're going to get from this URI. Finally, we can add some kind of encoding. For example, in this case, we just use URL encoding just to bypass some type of filtering in some cases that the shared target may perform in order to, let's say, filter the file name. And so this helps in many cases. Anyway, next, we return the result back to the requester. And finally, we have the other method here, which is the query. Again, we get the incoming URI. We get the path query parameter this time. And whatever this path query parameter, we're going to create a file descriptor and send it back to the requester. Finally, where we carry the payload, here we have many options. We can actually request the payload from a remote server, but we can also add it in our assets directory and copy it into the internal file directory of the app, of our rogue APK. So why we did all that, as I said before, to make things a little bit more general. So we can now just create a method which will get the package name, get the component and a URI, create the intent, and send it to the shared target. So we don't have any user interaction, we don't have anything. The last, let's say, part which I didn't explain here is how this URI should look from our point. So we have a content URI, content scheme, the authority, which is our content provider. We have a path that we are not taking under consideration in our queries or stuff, so it can be anything in our case. And then we have the path query parameter, which is the first parameter that will define the payload that we want to send to the shared target. That's the first one. Next is the name. In this case, I used some path traversal characters. Then we have the size. Again, can be modified dynamically. Then if we are going to encode or not the name in this case. So if we get a query like this one here, which uses the specific URI, we're gonna add this row in our, let's say, in our content provider. So our content provider is going to look like the entry that I have here. And when it comes to the payload, we're gonna send the file which is indicated by the path, as I said before. So, alright, so how we choose the payload? Now, what are we going to choose? Now, regarding the payloads, we are looking for cases where the application will load something from its internal storage. So if it loads some kind of a library from there, that's our best chance. And why it's our best chance? Because Android apps interacting with native code using a Java native interface. So what that means is that when a library gets loaded, the JNR load is the first method that is going to be called, and whatever code is there is going to be executed. So we're going to have our code executed by simply adding it into the specific method. So next we have the on-demand delivery modules, which is a Google's library. I'm going to go into details about this one. So I'm going to pass it for now. I'm going to give details during the code execution case. Finally, we have some kind of critical setting that we might write in the shared preferences directory. And when we get read access, because all that I mentioned here is having write access, we are looking for loose file providers or sensitive info which might be exposed in already, let's say, shared paths. All right? So that's another interesting case which came up out of this, let's say, research of ours. And was used actually to, let's say, escalate a simple write to an override when it comes to the shared preferences directory. So, simply said, in many cases we had an issue when we were trying to overwrite a file. And this issue was the following. The application was checking if the file exists and simply won't override it. Right? So this is a problem, because in many cases the app will involve the user to change the file name or will change the file name by itself, which is not helpful to us. So the behavior which I'm going to show you is the default behavior of the shared preferences implementation. So this is what happens when you're using the shared preferences and you're, let's say, starting your app. So the first thing is to get the XML file which has the specific shared preferences, right? And create another file which is called which is the same name, has the same name, and the back.back extension, right? Next thing is to call the start load from disk, which start load from disk is going to call it's going to check actually if the backup file exists. And if it exists, it's going to delete the original file and rename the back file to XML file. So what that means is that if you have this check here, the file exists, all right, you can simply write the same file with a back extension. So and let this implementation, this behavior to, simply delete the other file and overwrite, just copy yours. All right. So this actually is demonstrated in this case from this APK. Just some context before I start playing the demo. So we have an app which gets the settings from the shared preference directory, from the shared preference file. And the only thing that it does is giving a name. We're going to save it under the internal files directory. So it has, let's say, a protection. It checks if the file exists. It won't override it. And it has a vulnerability, which is a path traversal. We can simply, let's say, escape the default destination directory. So let's see how it works. So here, actually, you can say monitor how the files have been created and deleted in this case. Right, so we give the file name, it will save it in the files directory. Right, so simple, it has the specific content, right, when you create it. So if we try to override this file, the file exists, will block this override. And then we are trying to write something in the shared preference directory. The file exists, we won't override it, because it's the server settings. So when we restart the app, it will happen exactly as I described before. It will delete the XML file, it will rename our file to XML file, and it will get the server settings from our side. So this way we can simply, like I said before, we can, let's say, escalate a simple write to override when it comes to the shared preference directory. Now when it comes to reading, okay, actually what I said so far is about an app which can leverage this vulnerability type and get write access in the private directory. But what about reading? Yeah, and reading is also possible. In case, again, the application handles some kind of a stream. In this case, an action view in the intent filter using content scheme would suffice. And we are looking for misconfigured content providers. We are looking for loose file provider paths. And we are looking for, more importantly, we are looking where the app will cache the specific file, will cache the specific stream. Right? So what I mean, first of all, with misconfigured content providers, the app implements its own file provider and doesn't use the default one. And why this can be bad, right? It can be bad due to the fact that in most cases they don't check for something like that. They don't filter the stream. So you can just index any file within the specific, within actually the internal directory of the app. What will happen if you use a file provider, default file provider, is that it will throw an error saying that, you know, this file jumped out of the shared directory, so it will fail. This will fail. So it's better to use a default file provider. Now, what I mean by loose file provider paths. So remember the file path file. So we're looking for something like that, something that points to the root directory of the device or points to the internal root directory. Why? Because then we can index again files within the private directory and files that may have some kind of critical info for us. All right, that we may use. Last step, and the most important in this case, is where the app caches the specific file. All right, so if it caches the file in the external directory, we can pick it up from there, assuming that we have permissions. Many of you may say we have the restrictions which were imported in Android 10 regarding the scope directory, but there are many ways to bypass these restrictions. I'm not going to go into details, but there are ways. For example, the target SDK, you can just target the lower SDK and you can get your app opt out from these restrictions. So yeah, that's just one way. And then just modifying the display name query parameter. So this display name query parameter is used actually from the default file provider. So you can check something like that, right? Again, if the app doesn't sanitize this display name query parameter, which is default one, as I said before, then you may be able to, let's say, change the cache directory to a path that you control. So you can get the file, let's say, served to you, right? Given back to you. All right. So some statistics from the apps that we reviewed. From a sample of about 20 apps, which had the common characteristic of 100 million installs, more than 100 million installs according to the Google Play Store. 55 of them were found to be vulnerable. With, out of these 55%, we had code execution 28% of them. 18% was information disclosure and 27% was low to no security impact. And we're going to see the code execution that I said in the beginning of this presentation. So it's a browser. It's a browser which has more than 500 million installs, and it is a shared target, right? It uses an activity alias which targets the main activity and has the filter that I talked to you about before, the send filter with the action and data and all these things that we discussed so far. And what is the first step? as I said again, it will try to fetch the remote file name. So you will call the method h here. And whatever this method will return, will assign it to a value h11. And the next step was to create a string out of the incoming URI. Then it was using the string in order to get the hash of it, concatenated with the file provider, and all this to create a temporary file to cache the specific file, right? So that was the first step. But the next step was to get the first value from the remote content provider, concatenate it to the stream, and save the file there. So what happened is we simply send an intent which has which sends the following name, right? Just like some kind of, let's say, to see how the application will just react to this, how it will handle actually. And the result was to jump a couple of directories back and save it out of the destination directory. All right. So at this point we have write access. We can write actually whatever we want, but not overwrite. And this is where the dynamic module delivery comes into play that I said I'm going to describe. So Google Play uses app bundles to generate and serve optimized APKs depending on your device's configuration. So I don't know if any of you have created an Android app so far, but let's say you are creating an app using the legacy APKs and you want to support many devices, many architectures. You are going to include all the libraries to support this architectures, x86 or v7, v8, and so on. You may also want to, let's say, support different languages. You are going to include them all. But now, okay, that's very clever. We can use a bundle and we can deliver what exactly we want to each device. So your device is v7, v8 or something. We're going to deliver the specific, let's say, libraries. Okay, that's cool. And this can be used, as I said before, in order to deliver also plugins and stuff like that. And actually, this is a plugin case, in our case. So how we can see if an application uses a specific library, check for the specific package, and check for the split compat application in the manifest and Android manifest file. And then we can do some kind of static source code review to see if the use of the split install manager or the split installer request. And actually this is going to give us the name of the downloaded plugin, right? Or module or whatever is going to be added dynamically. So what happens now is, the interesting part here is what happens in the internal directory of this app. So this library creates predictable paths, right? So it's going to create a path under the files directory, which is called split compat. It will add the version of the package, and we'll add another couple of directories, the verified splits and unverified splits. So it will download the module and save it into the unverified splits, right? Then it will, let's say, unpack the APK because the module comes in the form of an APK. And if this has, let's say, native libraries, it's going to create another directory which is called native libraries. It's going to extract the native libraries there. Right, that's okay. But the first idea was actually to replace the native libraries, right? We can see what it downloads and we can replace it. All right. Yeah, but that doesn't work due to the fact, like I said before, the app may check if the file exists and won't overwrite it. So the other idea was the following. Let's add an APK that the application expects to load, right? Under the verified splits directory. And we had, let's say, a nice surprise that our APK was exploded. The native libraries were copied in the native libraries directory. And we were able, like I said, to get this file loaded. So our payload looked like the one I have here. So as I said, main cases, we had the send intent. We targeted the dog reader activity, the specific one. And here was our payload, which was an APK that had some native libraries that, let's say, correspond to a plugin that this app was using. And finally, we saved this, we forced the application to save this APK under the verified splits directory. So the next thing was when the user was trying to, load to unzip a file, because this was an unzip plugin. Our library was loaded, and our JNI the code in our JNI load was executed and we got access to the user's device. Right? This was about the code execution case, and now how we can secure shared targets from this and similar type of attacks. All right. First of all, we have to ensure that the incoming stream matches the intent filters criteria. I wouldn't say that this is something like, okay, we should rely on 100%, but it's the first line of defense, right? And then, if it is possible, we have to ignore actually the display name. You don't have to use the display name in order to cache the file, right? Doesn't make much sense. You can simply create a random name or something, just using a unique identifier or something, and cache the file, right? Now, in case you have to use the display name, then you have to take extra steps in order to sanitize the name. So, first of all, resolve any URL encoded characters, because you might have something like that, which, while you expect something like this, which is the shared preferences file, for example, to get something like that, you are going to have this, right? So you're going to carry the path traversal characters within. Canonicalize the file name in order to resolve any path traversal characters. And last step, isolate the path segment, the last path segment of the given file URI. Now, if you want to be more insane, you can take extra steps. You can create, let's say, some kind of regex in order to filter out characters that you might think that they are, suspicious or something. Yeah, so that was it. Thank you very much for your attention. Thank you.
So, can you little bit describe about pending intents?
Can I? Sorry?
Pending intents.
Pending intents.
Yeah.
It doesn't work with pending intents from the point that the shared target has let's say, a very fixed way of working. But, the pending intent thing works like if you send it to some kind of, using a notification service or something, and then the user clicks on it. It might work, but the standard way of, let's say, the more fixed ways is the one that I described here right now.
So, what are the attack vectors of pending intents?
Sorry?
Attack vectors.
Activities.
Attack vectors.
Sorry? Attacking vectors. I don't know. You can have whatever you think about, whatever. Like I said before, it might be any kind of shared target, like a mail app, like a messenger, like anything. If you try, like I said again, to long press a file and send a file or something, you can see any app which might be used for this kind of attack. So yeah, I guess it makes. Yeah.
So if we implement custom permission on all the components in the manifest file, instead of filtering the intent, getting data from the intents, so is it safe, or we have to filter the intents?
Can you repeat it? Can you a little bit closer, because I think.
So if we implement custom permission on all the application components like activity, receiver, content provider, instead of filtering the intents data in the code, so is it safe, or we have to also filter the intent data?
You mean the content of the file, right? Yeah. I would suggest that if there is such an option, but don't rely on some, let's say, methods which are already, let's say, use some kind of a framework method in order to get that, because they rely on extensions, file extensions in order to do that. And this can be, there are many ways to bypass that. If you can, let's say, verify the content using some kind of, check the header or something, why not? That's something extra you should do, yeah. Yeah,
but if we implement custom permission, then no any application can access that content provider or application component.
No, it can. You mean what? Not to export the content provider? What?
No. We are implementing custom permission.
The?
Permission level.
Custom permissions. Yeah. Okay. No. In any case, when you are handling data which is shared from, you have to have some kind of open points, right? You have, how you're going to receive this data. Whatever you do, even if you, let's say, implement your own permissions, whatever. Actually, these providers that I showed you before, I'm not talking about something which is exported, right? Everything is, they are all not exported. we are following let's say the safety measures that developers follow. But yeah, there is no, the protection doesn't come from the, let's say, permission side, right? You have to check what you are handling and how you are handling that. That's the point, right?
Any other questions?
But when it comes to the code execution scenario which you presented, you showed us that basically you were using that specific app which had the split APK stuff, but Android is not verifying the signature of the split APKs?
No.
So that's a vulnerability in Android, right?
Yeah, I don't know. I think
you don't feel that's a vulnerability?
They enforce those things. Yeah, they enforce those things upon download. But after downloading, the way that they assemble everything, they will have to sign like all of the different combinations for all different architectures and whatnot. It's impossible to do, like impractical, let's say.
So
they don't enforce and they can't practically.
The verification takes steps on the verified splits, but if you copy something on verified splits, it has some kind of a loop there which gets this folder and they simply explode it there.
Okay, I was feeling that it would have make sense like when opening the file, like trying to verify the signature again before unzipping or copying the files, but I don't know.
Okay, I think we have to wrap this up. You guys can talk about it more in the bar or at lunch. We need to get ready for the next session, so thank you.
Thank you very much.